All right, let's just jump right into it. Today, in this explainer, we're demystifying AI logic by surviving a deadly game. We hear a lot about the magic of artificial intelligence, but today, we're going to strip away the mystery and look under the hood at the actual mathematical engine. We are going to see exactly how a machine goes from knowing absolutely nothing to deducing complex facts about its environment to win.
You see, to really grasp how AI works, we first have to talk about knowledge representation. When a machine tries to solve a problem, it needs a way to formalize what it's dealing with. As our source material points out, a bad description using a bad representation is like hitting a mental brick wall. It completely blocks problem solving. It leaves our AI operating with, well, what this comic jokingly refers to as a tuna brain.
Which brings us to the big question: how does an AI actually think? I mean, you and I intuitively know how to solve problems, right? We look at a room, we see obstacles, and we just walk around them. But a machine doesn't have that spatial intuition. It relies entirely on symbolic logic. So how do we translate our real-world reasoning into mathematical symbols that a machine can actually use to uncover hidden properties about the world?
To figure this out, we're going to dive into a legendary AI simulation called the Wumpus World. Picture a perilous 4x4 grid cave system. Our AI agent drops into the bottom left corner, and its mission is simple but deadly. Navigate using only its digital sensors, find a pot of gold, and get out alive, all while dodging bottomless pits and the Wumpus.
This setup is perfect because it brilliantly lays out some strict logical rules. Here is the baseline knowledge our AI starts with. A stench means the Wumpus is in an adjacent square. A breeze means there's a bottomless pit next door. And glitter? Bingo, you found the gold. The stakes are highly quantified too. You get 1,000 points for the gold, but you lose 1,000 if you die. Every single step costs you a point, and firing your one and only arrow costs 10. Efficiency is absolutely key.
Now, before we make our first move, we need a quick refresher on how the AI processes all this. It boils down to syntax versus semantics. Syntax is just the grammar, the legal combinations of mathematical symbols. But syntax alone doesn't actually mean anything. That's where semantics comes in. Semantics maps those symbols to real-world facts, defining whether a specific statement is true or false in what logicians call a possible world.
Let's actually visualize these possible worlds or models. Imagine a boundary. Let's call it our knowledge base. Inside this space are all the potential layouts of the cave that perfectly align with the rules and the clues our AI has gathered so far. Every single model inside that boundary is a totally valid reality based on what the AI currently knows.
To keep from falling into a pit, the AI relies heavily on a crucial logical relationship called entailment. Basically, entailment means a conclusion absolutely must be true if your starting facts are true. So, if the AI looks at its knowledge base and sees that a specific square is safe in every single possible scenario within that boundary, then it knows, for a mathematical fact, that it's safe to proceed.
Let's see this in action through a process called model checking. By mapping out these scenarios, the AI deduces that square 1, 2 is 100% safe. Why? Because when you look at every single valid scenario where the AI's current observations hold true, there isn't a single one that contains a pit in that square. The knowledge base perfectly entails the safety of that spot.
So the big takeaway here is that this mathematical engine of propositional logic is exactly how the AI processes those possible worlds to make decisions. It uses standard rules of inference, things like Modus Ponens, for instance. If the rule says P implies Q, and the AI knows P is true, it just securely locks Q into its knowledge base. It doesn't even have to manually check every possible universe anymore. It just knows.
All right, let's play this out dynamically. Our agent drops into the start square at 1, 1, it turns on its sensors, and gets nothing. No stench, no breeze, no glitter. It didn't bump into a wall, and it didn't hear a scream. It's alive, so square 1, 1 is clearly safe.
But watch what happens next. Because the rules dictate that pits cause breezes in adjacent squares, the absolute absence of a breeze here gives the AI a massive clue. It mathematically deduces that the square directly above it and the square directly to its right are completely safe. It can confidently step forward without guessing.
So the AI decides to move right into square 2, 1. But here's where things get a little tense. The second it steps into this new square, its sensors pick up a breeze. Uh-oh. Remember our environment rules? A breeze means there's a bottomless pit right next door.
So what do we do next? The AI's propositional logic engine kicks into high gear. It knows it just came from 1, 1, which is definitely safe.
That means the pit causing this breeze must be in either the square directly above at 2, 2 or further right at 3, 1. Both of those spots get a big, scary question mark in its knowledge base. The risk is just too high. A purely logical agent doesn't gamble, so it retreats back to the start to try the other path.
Taking the upper path this time, the agent moves into square 1, 2. Okay, no breeze here, but its sensors pick up a terrible stench. Yuck. Based on the rules, a stench means the Wumpus is adjacent. It knows the monster isn't at the start, and it deduces it's not at 2, 2, which leaves only one logical hiding spot for the Wumpus, square 1, 3.
But wait, here is honestly the most beautiful piece of logic in this whole run. Remember how square 2, 2 was flagged as a potential pit from our earlier breeze? Well, there is no breeze right here at 1, 2. If there were a pit at 2, 2, we'd definitely feel a breeze right now. Because we don't, the AI elegantly deduces that 2, 2 is completely pit-free. It literally solved the mystery from the other side of the map. How cool is that?
Armed with this harder knowledge, the agent knows 2, 2 is totally clear. It moves there, and then steps up again to 2, 3. Suddenly, its sensors go absolutely haywire. It detects a stench, so the Wumpus is close. It detects a breeze, another pit nearby. But most importantly, it detects glitter. It found the gold. Now, grabbing the gold is great, but the job isn't done. It still has to get out alive. So it checks its internal knowledge base, which is now a beautifully mapped out representation of safe and unsafe zones. It plots a safe route backward, moving through the squares it knows are secure, and waltzes right out the starting door, scoring a massive 1,000-point victory entirely through mathematical deduction.
Our AI survived the Wumpus World, which is awesome, but the basic propositional logic it used actually has some pretty severe limits. Honestly, it's incredibly clunky. You'd need dozens of specific sentences just to map out the relationship between the Wumpus and the stenches for every square, and at least 64 sentences just to describe the effects of basic movement. It struggles to handle general patterns or multiple objects, making it way too rigid for the infinite complexity of the real world.
Ultimately, representing knowledge the right way is absolutely everything. As the source material beautifully summarizes, a good knowledge representation is an open door to true problem solving, whereas a bad one is a straight-up brick wall. We gave our AI the perfect logical representation for this tiny, restricted grid, and it proved it could literally think its way out of danger.
Which leaves us with a totally fascinating challenge as we look toward the future. If basic logic is just too rigid, how do we level up an AI to grasp things like time, space, and dynamic relationships in the real world? The answer lies in something called first-order logic, and honestly, that is the exact threshold where simple computer programs transform into the intelligent systems that are shaping our future. So what kind of world will they deduce next? Something to think about.